All right. So thanks a lot for having me here. Yes, I'm going to talk about some recent developments on the so-called generalized hydrodynamics. I don't know if you've never heard about that. It's just a hydrodynamic theory for integrable spin chains with some application on computing transport. So this is going to be really a talk about transport in a very specific set of models, but and so non-equilibrium and also the problem of understanding diffusion. So the whole field started a bit like, if you want, like a decade ago with some papers that pushed really like the idea of studying non-equilibrium physics in closed systems. So non-equilibrium time evolution induced by unitary time evolution. So in a sense, usually when you have a closed system, you study the equilibrium physics like correlation function on the ground state or the low line excitations. This is to tell you like how the system responds to perturbation. But the non-equilibrium physics is usually a study of higher excited states in the spectrum, which is mostly unknown territories because you cannot use in generally like field theory methods. And one of the most used methods, at least in theory, but also in experiments, of studying this part of the spectrum is by performing a quantum quench. You prepare a state, you prepare your system in some state, and then you let it evolve with the unitary time evolution. And most of the focus of the last decade of the studies has been in, for example, in understanding the emergence of local steady states, right? I mean, the evolution is unitary, so the whole system doesn't relax. There is no thermalization for the whole system. But if you focus on the subpart of the system, namely on correlation function of local operators, you may see some thermalization. So like you may see that there is some effective local statistical ensemble that well reproduce the expectation value of correlation at large times. And these ensembles can be just Gibbs ensemble, or in some cases, can be generalized Gibbs ensemble, called GGE, in case you have more than one conserved quantity. And so one of the quantum quenches are a very wide topic. I mean, your initial state can be some states that is not an eigenstate of your Hamiltonian. For example, this is the spin chain. You can choose, for example, I don't know, all the spin in some direction and let it evolve. But recently, there has been a study also in what are called inhomogeneous quenches. So in a sense, your initial state is not translational invariant. And the easiest implementation of this is by doing a bipartite quench. For example, your initial state is a tensor product of two states, a left state and a right state. In a sense, this is like the old problem of statistical mechanics, or like having a hot bath and a cold bath and seeing what, and then you release and see what happens. There are a number of people that studied this type of quenches. In a sense, the whole field was a bit like also, I mean, a big contribution to this topic was the works of Benjamin Doyon and Denis Bernard. 2012, they studied this problem in conformal field theories, which is, so study, for example, what's the energy current that flow between two CFT at two different temperatures. And so the question was, indeed, can we compute what's the current in generic systems, or at least in spin chains, okay? So the picture already intuitively you can think is the moment I join these two states, if I have a spin chain and the interaction is local, there is always a maximal speed of propagation for the quasi-particle. This is guaranteed by Lieb Robinson. So there will be a light cone. There will be a light cone, so outside the light cone, nothing changes, at least if the state is stationary, for example, like a thermal state. And inside the light cone, there will be some non-equilibrium time evolution, okay? But, and the whole, so in a sense, if you can say, okay, I will wait long enough, I will wait some time, and this time I will slice my system position X, and I want to see, for example, what's the profile of a local observable. For example, the current, energy current. Now, if I join a two-temperature state, what's the profile of energy current inside the light cone? Is there a way to extract this For example, can I formulate an hydrodynamic picture to extract this profile at large time? And this is why to study this problem. Well, to study non-equilibrium transport, for example, in a spin chain. Well, no, it's really hard to find exact result, or at least really analytical or quantitative result for energy current flowing on a spin chain at 2 different temperatures. But also to study really the linear response of the system. So this is non-equilibrium, but you can also go back to equilibrium by doing small perturbations. Now you can imagine that you take your spin chain and you prepare it 2 different, slightly different baths, like a bit more energy, a bit less energy. And this is, you study then the linear response, the flow, the linear current, the flow in the system. These are ways to study transport coefficients that are called, for example, the Drude weights, like, for example, how much current flow in the system if you do a little unbalance. Very highly studied, for example, in integrable model, because integrable models are somehow a superconductive system. So they have a finite Drude weight. How much to evaluate this is not easy. But also to compute, for example, local correlation functions. So I really like spin-spin correlation functions. It's in presence of interaction is a very complicated topic, but you can use this method to reconstruct a bit of this. But also generic system, we know that exhibits a type of transport which is not ballistic, is diffusive, right? The most common type of transport is just diffusive transport, namely that the current increase not with time, but with the square root of time. And so the question is how to understand the emergence of diffusive transport really from the microscopic interactions among the elementary constituents of the system. And if we can use integrable models that are very specific models where we can say something analytically to understand a generic property of system, which is indeed, for example, diffusion, diffusive transport, which is a property of any generic interacting system. And we see that the answer is yes. And this is a bit the outline. So I'm going to talk about, present this idea of generalized hydrodynamics. We work already now of 2 years of a number of people. I forgot in the audience. Bruno Bertini will be in the audience. Mario Colura will not. And how do use this to reconstruct Drude weights, which are transport coefficients in spin chains. They work with the Navier-Stokes also in the audience. So we give a talk, probably also talking about this. And how to indeed see diffusion in integrable models. This is usually 2 words that do not go together, because integral model is seen as a very specific model where there is no thermalization. So thermalization, there is no diffusion, but actually you can find diffusion. Thermal models work with the Nibber-Narbridge and Mondrian. And if I have time also to see how in some cases, if a very specific point, you don't have just diffusion, but you can have super diffusion, like some form of some different universality class, which is not the Gaussian, standard Gaussian fluctuations. Okay, so just to give you a quick review of what are generalized Gibbs ensembles, actually the formulation that I like more is the so-called microcanonical Gibbs ensemble. Namely, I mean, you have your quantum quench, your system is in some state beside 0, you let it evolve, and then after the system is relaxed, you can really picture your system in some local steady states, right? And if your initial state is homogeneous, namely is translation invariant, all these steady states are the same, right? So once I found one, I found all of them. So this characterizes now a local correlation in this subpart of the system. And now to fix it, well, this is fixed by the local conserved quantities, because it's a local steady state, okay? So I have a number of local conserved quantities. I don't know, now I write n, can be 1, 2, 3, 4, or infinite, case of integrable. I have to evaluate the expectation value, and this fixes me the microcanonical G. This is just, you can just say that here, locally, the system is equivalent to be in one of its eigenstates, like, for example, a thermal eigenstate, is the case, for example, in an eigenstate thermalization hypothesis. That is equivalent to say that the system locally is described by a statistical ensemble of this form, just a Gibbs statistical ensemble where there are a number of chemical potential associated to the conserved quantities. This is just a canonical Gibbs ensemble. And this is indeed the picture that you have when you do homogeneous quantum quantities, and in general, these are called generalized Gibbs ensemble. Macrocanonical because you can represent these ensembles simply with an eigenstate. Now, if I put some, if now I take my initial state which is not translation invariant, for example, I have indeed some spin chain with some space modulation of, I don't know, magnetization, and I want to see how these evolve. Well, now you can imagine that at large time I will still relax to some local steady states, but the local steady states are not anymore space and time independent. For each, let me call it fluid cell, so some indeed region big enough for the system where particles are locally relaxed or thermalized or generalized thermalized, I can introduce an eigenstate that will describe the system locally here, but it will depend on space and time. Why? Because the local conserved quantities, I can decompose it in local conserved densities, and in each part of the system there will be different local conserved densities. So for each x and t, there will be different local conserved densities, and this completely specifies my state locally in position x at time t. Okay? So now the whole idea of hydrodynamics is to say, well, let's assume that this relaxation time is really small. Let me put it to 0. And the whole dynamics I care about is the evolution of the macroscopic degrees of freedom. So I don't care anymore about the macroscopic, because I just assume they relax to some local stationary state, local quasi-stationary state. I will just write some differential equation of the type with some nonlinear differential operator that act on the expectation value of local conserved densities and give me the evolution of these fluid cells. That's how the expectation value inside the chain evolve in this large time modulation, which is much larger than the relaxation times. Okay? But this is just standard hydrodynamics. But now we will specify to a set of model, well, we have a control on these local steady states. In a sense, we will talk about integrable models. So an integrable model is nice because we have a quasi-particle picture. What does it mean? It means that each eigenstate, okay, each eigenstate of the model specified by a set of conserved quantities in the thermodynamic limit can be written simply as a quasi-particle content. What is a quasi-particle content? It means that you fix the type of quasi-particle you have in the system, which can be not just one type, but you can have different types. Right? For example, this is for a spin chain. You can have just manyons or bound states of manyons of different size. By the way, for each of these quasi-particle type, you have a number of quasi-particles and a large number such that you can, for each momentum, quasi-momentum, you can associate just how many quasi-particles there are, which are called the density of quasi-particle. There are density of, which are specified like this, so density of particle with a given particle number at position x and t, and for any momentum theta, or rapidity is called, or theta. And if you wonder how many quasi-particles I have, well, you just have to look at your Hamiltonian and take the group symmetry of Hamiltonian, and then for all irreducible representation, you have a quasi-particle type, really like as it is in a standard model. For example, if you have SU2, Heisenberg chain, you will have a quasi-particle type for any irreducible representation of SU2, so you have an infinite number of quasi-particle types. And any conserved quantities can be written as just the sum of the density times some single particle eigenvalue for each of the particles. Okay, this is great because now I don't have to work anymore with eigenstates, which are a bit, I wouldn't know how to do it. I have to work now with quasi-particle densities. So can I write now a continuity equation for the quasi-particle density? And the answer is yes, and this is the whole idea of generalized hydrodynamics. So I write a continuity equation for my conserved quantities. These are current associated to the conserved quantities, okay? And now I do hydrodynamic assumption. I assume that this operator, I mean the expectation value of this operator have a weak time and space modulation. So in a sense, I don't care about the equation per se, for the operatorial equation itself, but I only write an equation for the expectation values of this object. This is, if you want, really the hydrodynamic assumption. And now I want to write these two objects in terms of the quasi-particles. Okay? So the expectation value of the concept quantities, I know how to write it. It's just the sum over all the quasi-particle given the density times the single particle eigenvalue. But the question is, how do I write the current? Well, it turned out, in these two papers, turned out that the answer is quite easy. You just have to take the way you write the content of the charge, you just multiply times a velocity. Really like in standard dynamic, if you have some density rho, the current is obtained by multiplying the density times the velocity. What is this velocity? It's just the effective group velocity of the quasi-particle, namely the derivative of the dispersion relation respect to the momentum. Now, these two objects actually, in presence of interaction, they depend on the density of quasi-particle. This phenomenon is called dressing. We'll see later. So this velocity is actually a functional also of the density. So it's not that simple to compute it, but still, nevertheless, you can do it. And now I can use this relation to write this continuity equation in terms of the quasi-particle. So this is a continuity equation. This tells me that the time derivative of the density of quasi-particle is simply equal to the divergence of the time of the density quasi-particle times their effective velocity. It's exactly what you would expect. And this is 0 because I just did an approximation. I just said that the current is simply given by this formula. In principle, I will have extra terms to this equation that will give me some correction to the current, smaller scales. Anyway, this is the mother equation of what's called generalized hydrodynamics. Why generalized? Simply because it's an hydrodynamic with an infinite set of conserved quantities. It's not just standard hydrodynamic where you have just energy or momentum. Here there are many conserved quantities, one for each quasi-particle. It's really incorporating the fact that this quasi-particle has stable excitation that travel with a fixed velocity. Okay? But this is great because at least I can solve this problem of computing expectation value of observable large time, at least for an integrable model. Indeed, this equation can be reformulated in terms of the occupation number, which is just this function density quasi-particle divided by the total density of state. And at large time, you can see that everything becomes a function not of space and time, but space over time. And this is just telling you that if you have some quasi-particle content on the left, some quasi-particle on the right, well, then if you're here on a specific ray, you will see the quasi-particle coming from the left if they have enough velocity to come from you from the left. Otherwise, you will just see the quasi-particle from the right. Very simple solution of the equation, which allow you to reconstruct, for example, a profile of a car of this is profile of energy density as a function of x over t. So this seems very easy. This is simply a very easy question, but at least for interacting case, was only solved 2 years ago, thanks to this generalized hydrodynamics. This is for a spin chain, some value delta. You have some profile of energy as a function of x over t. These are different value of interaction, and the dots are Diamond-G simulation that goes on top of the solution, hydrodynamic solution. So hydrodynamic is not valid only at infinite time, so it's already good finite time, as the numerical simulation shows you. But okay, so going a bit fast here because maybe it's a story that now already 2 years ago. Then one can use this to compute, to indeed understand transport. Okay, transport, and one of the coefficients that are very much interesting in transport theory are the so-called Drude weights. Now, we are going to do a little bit of balance. We're choosing do a spin chain where on the left we put a little bit more charge. Whatever is charge can be energy, or can be spin, or can be electronic charge. And on the left a little bit less. And the Drude weight is defined like that. It's just the total current. You wait, and then you integrate the current as some time t, okay, over x. And you take the large time limit, so you put this time large, and then after you take the large time limit, you send this inhomogeneity to 0. Okay, so this Drude weight, just how much current will flow into the system when I do a little bit of balance, just linear response. And generalized, you can now use this continuity equation I show you to arrive to a closed formula for this Drude weight, which is again obtained as by summing over all the quasi-particle, weighted by their densities, times the velocity and the so-called dress charge. So the dress charge is like the single particle eigenvalue of the charge, but dressed by the presence of all the other particles. So T is the scattering kernel of the particle. So particle flow into the system, but many times they scatter. Okay, and they scatter with the scattering matrix given by T. But scattering is elastic, so the presence of many particles can be resummed. Resum in the so-called dressing is an integral equation that, given the single particle eigenvalue, like for example the single particle energy, give you the dress eigenvalue. And this tell you what's the Drude weight of the system. So some people already computed in the 90s, like Professor Zatos, for some system like spin chains. But now this formula, it's very easy. You can use it for different setting. For example, in this model, XZ chain, which is somehow the simplest interacting spin chain you can think of, just a model of spin hopping with interacting with the delta. This is an integrable model in the sense that it has some ballistic propagation. Okay, so now you can do this kind of phase diagram as a function of delta. Delta is the interaction, or if you want, the anisotropy, and H, which is the external field. And whenever H is non-zero, you are basically breaking the spin flip symmetry, and you always have ballistic transport. So in a sense, the system, there is a spin current is ballistic. The system is a superconductor. It's interesting when you put the field, the standard field, to 0, so it's called half filling, because then if you're in the so-called gapless regime, when delta is between -1 and 1, you still have ballistic transport, which is really a feature of integrability. But if you're in the so-called gap regime, transport is not ballistic anymore, is actually sub-ballistic and generalized diffusive. Now, was already quite a hard question how to compute the Drude weight in this region because it's very interesting, right? I mean, you have a point where you are filling, so there is spin flip invariance, but still you can have a finite ballistic transport. This is really interesting. It means that there is some conserved quantities which is not spin flip invariant. Anyway, with generalized hydrodynamics you can compute it, but there were already some results from Prosen and Elievsky where they managed to bound. They managed to bound this Drude weight using some conserved quantities. And they found this quite striking result where basically the Drude weights, that again is a physical quantity, strongly depend on the value of the anisotropy. So it's called a nowhere continuous function. What does it mean? It means that depending on if you choose delta as cosine of pi m over n, you have a very different result depending on m n. So it's not a function of delta, it's a function of n and n. On the other hand, if you go on the real number, so if you take like the limit of large m n, you have just a smooth profile. It's a very strange function. But it's really depends on the, as I said before, depends on the quasi-particle content of the system, which here it's represented by the Q-deform SU2, which has a very strange unitary irreducible representation. Anyway, this is in the case of Prosen and Elievsky, they thought that this could be just bound, but with generalized hydrodynamics now, it was possible just to say that this is not the bound, this is actually the exact result at infinite temperature. If you decrease the temperature, then these discontinuities get smoothened out. Eventually, at 0 temperature, this plot is completely continuous, and you recover Bose-ionization results. Anyway, there is another model which is integrable, but very interesting and very hard, which is the Hubbard model. It's a model for interacting electrons on a chain where interaction is local. And if you try to compute something on this model from integrability, you really can spend 10 years without having much results. But at least now, generalized dynamics, the nice thing of this equation, this continuity equation I show you, is that it's completely universal. It works for any model where you can define a quasi-particle content. So also in this Hubbard model, which is quite hard, and you can compute indeed Drude weights as a function of the filling. The charge Drude weight is a function of the filling, or as a function of magnetization. This is the thermal Drude weight, it's a function of the temperature. Are there questions up to now? Okay. So, but Drude weights are interesting objects, but of course they're very related to integrability, right? I mean, a generic model will have unless it's not a superconductor, will have 0 Drude weight. There's no ballistic transport, as I said, in integrability. Now, sorry, in outside integrability, generically. But so we want to understand a bit more about diffusion, diffusing transport. And it's not really true that here there is no diffusion, in the sense that generically, this light cone picture that I show you, it's true that at a large time you only see the light cone, but if you actually look at a smaller time scale, you see that this broaden up with some time scale, which is usually which goes with the square root of time. And this is really a phenomenon due to interaction. So can we use the machinery of quasi-particle? Can we understand diffusion from the quasi-particle point of view? Now, if you want to do this, you just have to say, okay, I wrote a continuity equation for this object, like for the expectation value, charge, and currents. And I gave a first answer for the expectation value of the current. It's this formula I show you, right? It's just the charge times the velocity. But if I want to go to a smaller time scale, I have to introduce a so-called diffusion operator, which is some matrix which now couple the current of the charge I with the expectation value of the charge J for any I and J. This is a theory which has been developed in the 70s, 80s. Herbert Spohn gave a large contribution. It's mostly fall in the name of linear fluctuating hydrodynamic. And this is, in a sense, you don't have to think too much. It's, well, you can just redo the steps, but it's just telling you that if you have some type of diffusive correction to your charges, which have this form, then if you want to compute this matrix, this operator, which we call diffusion operator, well, you then have to compute just current correlator. So this D operator, once is multiplied times C, which is just a matrix of susceptibilities. These are objects you can compute just from standard thermodynamics. Then, if you multiply these two operators, you get this operator for any I and J. I and J are the index of the conserved quantities. Remember this. This is obtained as the integrated current correlator. So, if you're familiar with Kubo formula, this is nothing else than just Kubo formula, right? If you Kubo formula for a diffusion constant, just tell you that diffusion constant, well, Kubo and Einstein relation, if you want. Diffusion constant is given as 1 over susceptibility times integrated current correlator. Now, Kubo formula is for generic systems, so usually generic systems have 0 Drude weight. If they have finite Drude weight, all you have to do is simply subtract this Drude weight from the current correlator. This is still a valid definition of diffusion constant. What does it mean? It means that your system has ballistic transport, but has also diffusive properties. And you want to evaluate the diffusion constant of this system. Okay, so the question then is to evaluate these correlations. How much time do I have? 20 minutes? Okay. That this operator exists. You're just doing some. If you want, gradient expansion of your current current around the values of your charge. This is computed on some stationary state exactly. Yeah, this is, of course. This is the whole idea of a linear fluctuating hydrodynamic. You compute these diffusion constants in a stationary state, and then you generalize to a space and time modulation. No, sure. I mean, these are just the diffusive corrections. If you want to evaluate diffusive correction, this is the This is the definition. There can be other type of corrections, of course. Okay, so now the whole question now is to compute current-current correlations. Now, computing current-current correlation for a generic generic system is almost impossible. Then it's Kubo formula. You need to use perturbation theory and so on. Then you would say, okay, let's do this first for free system, like free fermions. Well, for free fermions, you would get simply that this is equal to 0. Okay? This is simply telling you that any free system, free fermion, free bosons, diffusion constants are always 0. Okay? There are no correction of these types. There are other corrections that usually have higher derivatives. Usually, depends on the setting. But there are no diffusive corrections. So you really have to work now on interacting system. And that's what is hard. Anyway, you want to compute, given some stationary state, which a stationary state is given by some quasi-particle content that I write like this. You want to compute these correlators. Now the standard way to do it, if you don't know anything, is by performing a form factor expansion. What is form factor expansion? Is simply that you don't know how to resolve the time dynamics of your operator, so you just insert a resolution identity here in between of eigenstates of your Hamiltonian. This way, you can resolve the time evolution of the operator. Now, what is this resolution of identity? In general, it's very hard to perform this spectral sum. Okay, this is called spectral sum. But here we have some friend which is telling us that the only intermediate states you have to include are called particle Hall excitations. So what are particle excitations? It's just telling you that you have your reference state, which is some quasi-particle state. So there is some quasi-particle content described by some density of quasi-particle. And all the intermediate states, all the excitations that are relevant from the point of view of local operators on this state are simply particle excitation. Namely, you take one particle and you change its momentum. You call this Hall and you call this particle. Okay? And you sum over all possible type of particle a Hall, namely all the possible number of them. You can do 2, 3, 4, 7, infinite number of particle excitation, and you sum them, and the sum is weighted by the so-called form factors, namely the matrix elements that tell you this local operator, what's the probability that creates this quasi-particle excitation. Okay? This is just formal expansion. It's very known in field theory to compute correlation functions, and in general it's very hard to compute because these form factors are usually complicated objects that strongly depends on the microscopic of the model. But turn out that from the point of view of diffusion, diffusion is a large scale property. So you don't really need to know really a lot of the form factor. You only need some information which rely in the so-called form factor poles. So I'm going to tell you about the form factor properties that you need. You just need a continuity equation that just tell you that this form factor, the form factor of the current are proportional to the energy difference, namely the energy of the excitations, and the form factor of the charge are proportional to the momentum of the excitation. This is just follow from continuity equation. And you use the so-called kinematic poles of the form factor. Now, this is very known for everyone working in field theory. It just tells you that if you have some form factor with some generic excitation, particle a Hall, and you take one of the particles and you put it very close to the Hall, well, then this form factor has a pole, has a single pole, namely diverge with 1 over the difference of particle a Hall, and the residue is actually fixed by, at least in field theory, is fixed by so-called form factor axioms. Tells you that the residue is given by the form factor with one less particle in a Hall times the so-called scattering matrix of the theory. Now here we are going to use a generalized version of this kinematic poles. So we're going to just tell you that instead of taking the simple scattering matrix, we take the dress scattering matrix. Dress because there is the presence of non-trivial background. So here we are not like in field theory when we just create 2 excitations, we let them scatter and we see what's the result. We have a continuity of excitations which dress everything because every particle scatters, and we take 2 of these excitations in this background and we let the scattering. So the presence of all the other, effectively dress the scattering matrix. And that's great because only these 2 properties are enough to obtain all we care about, namely diffusion. So the one particle Hall excitation actually turned out to give completely everything about ballistic transport. So ballistic transport is only the effect of having one particle excitation in the system. And this is intuitive because in free system, in like free fermions, you only have one particle excitations. And indeed, you have finite Drude weights. And the two particle excitations actually give you entirely diffusion. And two particle excitation is actually a feature of interacting system. There are no two particle excitation in free system for the operators, for the conserved operators. Actually, if you integrate all the other number of particle excitation, you get 0. And this is great because it means that diffusion is completely given by two particle excitations. And anyway, using all this, you manage to arrive to an expression for this diffusion matrix, which you can write in terms of the density of the quasi-particle, their effective velocities, and the dress scattering matrix. Here, okay, F is and you can also change the statistic of your quasi-particle. If you want fermions, this F is just 1 minus the occupation. If you want boson, F is 1 plus occupation. If you want classical, if you have 1. In general, it's very hard to know what's the real statistic of the quasi-particles, but at least for spin chains with XZ, Hubbard, you always use fermionic statistic. Anyway, you don't have to memorize this. The take-home message is that you have derived now an hydrodynamic equation for the motion of the quasi-particles, okay? And what you have learned that this quasi-particle propagate with some effective velocity, okay? We call that effective velocity, which is dressed by the presence of this non-trivial bath. But they don't only propagate. Their trajectory actually also broaden up. It broaden up, as you expect, with correction, with diffusive type of correction, namely with square root of t, due to two-body scatterings. So this is very similar to what happened when you write down Boltzmann equation. You have two-body scatterings that eventually leads to the thermalization of the system. And here it's very similar. There are no more than two. If you look at these time scales, square root of t, you only see two-body scattering between quasi-particle that completely give you this broadening up of their trajectories. And this two-body scattering is actually weighted by the scattering matrix of the model dressed by the presence of a non-trivial background in each fluid cell. What does it mean? It means that the way how particles scatter in this fluid cell or in this fluid cell, it can be very much changed because it depends on the density of quasi-particle in each density. For example, if you have more particle, the scattering can be enhanced, or if you have less particle, the scattering can be less. Okay? So it's really this effect of dressing due to the finite density of quasi-particle in each fluid cell. And this completely gives you what you can call Navier-Stokes equation, well, following just usual hydrodynamic notation, but GHD, generalized, because again, you are working with an infinite set of constant quantities, or if you want, a full density of quasi-particle. Anyway, this is an equation that now accounts for ballistic propagation and diffusion. And you can run it, you can solve it, and play a bit with this. For example, you can check with numerics, no? Like the MRG. You can ask the MRG friend to prepare to take a two-spin chain with XZ, for example, with some delta, which is cosine of power 7, or just close to 0.9. Your initial state is just, on the left, you put this density matrix, to mu sigma z. So you polarize a little bit your spin on the left with mu, and you polarize your little spin on the right with minus mu. You can take mu small, so you can work in the linear regime. It's easier than to solve this equation. You can use Fourier transform. And this is your profile of magnetization. So you see on the left, you have 0.5, just divided by mu. The right, I have minus 0.5. And you see the domain wall melts, right? It melts, but it melts with diffusion corrections. And it did this. So the dots are the numerical predictions. The dashed lines are simply taking this equation, just taking ballistic propagation. So of course, the domain wall also melts a bit ballistically. So it expands with some fixed velocity. But it has like error function correction on top of it that are well reproduced by this term. So if you don't put them, you see that you're very far. This would be like at time 40. This would be the prediction of only the ballistic, or if you want the Euler hydrodynamics. If you add these dissipati terms, you see that you fall on the correct result. Okay. Actually, if I have time, this is very similar to what happened in a very famous model of statistical mechanics, which is called the hard rod gas. This was studied again by Spohn and other people in the 90s and the 80s. It's a 1D model of classical 1D model of rods of size A, which scatter, and every time they scatter, they basically jump of length A. And so this, you can imagine, change a little bit their velocity, and indeed this means that there is an effective scattering matrix, which is proportional to A, indeed, which is actually is a constant, the velocity. And there is a dressing for the velocity, because indeed you see that the velocity is affected by the interaction. And if you use, in the 90s, these people, amazingly, they managed to compute this diffusion operator as a function of the velocities, as a matrix of the velocities of these rods. In a sense, this model is very simple, but still display ballistic transport and diffusion. So it's an interactive model. It's very not easy to solve it, but they managed to do it. And they also show that it's a Markov operator. As we heard this morning, indeed, diffusion, it's a Markov process of changing randomly velocities in the system. And quite amazingly, we found that this result for a quantum system, but if you put your scattering matrix simply equal to A, as is faking like a hard rod system, you find the same result that in the 90s was found for a hard rod. And even if you're familiar with the Lieb-Liniger model, it's a model for interactive bosons, and there is a coupling constant, which is C. If you take it quite large, well, if you take it infinity, it's just equivalent to a free fermion model. If you take it to order 1 over C, this is the scattering kernel becomes just a constant, like an hard rod gas, and the diffusion operator becomes exactly the same as the one for a hard rod gas. So the Lieb-Liniger model, a large coupling, is completely equivalent of a model of hard rod gas, also from the point of view of how particles diffuse. So this all this quantum model shows you, and this is actually again a Markov operator. So this, even for the full quantum model, this diffusion operator is a Markov operator. So it's telling you that there is not, this is purely classical process, namely this quasi-particle are scattering, and they have like some random process that randomize their velocity, and from there comes the diffusion. So in a sense, you reproduce exactly what you expected, but it's quite non-trivial to find the close-up formula for the diffusion operator in terms of quasi-particle. And another feature of diffusion is actually that it makes entropy increase. This is quite a bit contradictory, but with the fact that we are looking at the closed system, right? Here there is no external bath. The system is isolated. We are looking at the hydrodynamic description of the system, but still the total entropy, which you can write in terms of the quasi-particle content. This is a formula that's well known. It's called Yang-Yang entropies. Give you the entropy of each fluid cell in terms of the occupation of quasi-particle. You can show that the total entropy increase in time. It's always positive, as long as the diffusion operator is non-zero. You can understand this really like as a production of entropy in each fluid cell. This because diffusion smoothen out things, so you have a loss of small-scale structure. In each fluid cell, if you have some rapid variation of conserved quantities, diffusion is smoothen them out, and this causes an amount of entropy. Okay, yes, I guess I... Okay, just to conclude, diffusion is a generic subballistic transport, but there is also some, actually some different universality class, which is the case, for example, in an XYZ model when you strictly fix delta to be -1 or 1. In these cases, you can really show that these are super diffusive points, namely the diffusion constant for the spin diverge, and now we have an analytical formula for the diffusion constant, we can really see this. And this diversion is really due to the fact that you have a large number of quasi-particles, and if you sum the contribution to the diffusion constant of all these quasi-particles, you actually get infinity. And together with Nate, Prozen, Marco Mejendak, actually, we arrived to this result with a different approach by bounding the diffusion constant. I actually found out quite surprisingly that in any integrable model, which are the model where we can do calculation, in all the isotropy points, like Hubbard, Fermi-Hubbard, TJ chains, or any SUN chain, display superdiffusion. Diffusion constants diverge. Always due to infinite number of bound states. So there is not just diffusion, there are also superdiffusion that needs to be understood. And numerically, there have been also evidence of, in a XYZ chain, a delta equal 1, the exponent doesn't seem to be just 1/2, but seems to be 2/3, which is the exponent of KPZ, Kaldar-Parisi-Zhang universality class. So it seems that in 1D we can observe diffusion or superdiffusion depending on which universality class we are, but this is really far from being understood. Okay, so conclusion. I show you, I hope I convince you that this is a full hydrodynamic description of integrable model that include ballistic and diffusive transport. It's useful to solve the bipartite quench. It gives you exact computation of Drude weights on any stationary state, finite temperature, finite filling, zero filling. You can also compute now diffusion constant, which is quite non-trivial, and which I didn't show you, but you can imagine that this also gives you asymptotic dynamic correlation, dynamic structure factor. All this with a very intuitive quasi-particle picture. Questions? Well, big question is, we observe this superdiffusion when the interaction are isotropic, SUN, SU2N, graded or not. Is this due to integrability, or we can observe it also in generic system? Maybe also in generic system, you can see that if you set your interaction to be SUN invariant, take an SUN non-integrable chain, you can still see superdiffusion. And okay, now the big question, we compute diffusion. Diffusion is a big step, a little step if you want to understand thermalization, right? Because now at least particle scatter. But if you want, for example, compute really real thermalization, or like compute what happened in a generic system, can we break integrability? Namely, can we make quasi-particle decay? Can we still have some scattering, but then introduce some effect that lead to quasi-particle to decay? This is very hard, but it would be great, because really now we would have a complete description of a generic system from the point of view of the quasi-particle. And with this, I finished. Thank you very much for your attention.
Okay, questions? Thank you. Very interesting talk, but I'm also quite confused about many things. Maybe I'll have to ask you some more detailed questions later, but let me make a start. So you specifically you refer to the Lieb-Liniger model in a strongly interacting regime close to Tong-Shirado, and so are you predicting that there is actually diffusion in this model? Is that right?
Yes, at order 1/c square. Okay.
1/c square.
The diffusion constant, the first non-trivial order is 1/c square. So if you look at the 1/c, you don't see diffusion. You just have a free fermions elite dress, but quasi-particles are still free. You have to go to order 1/c square to see the first effect of diffusion.
Okay, I still have to digest that a little bit. It might be related to what I will be talking about on Friday, but anyway. So what are the quasi-particles that you're actually using here for the Lieb-Liniger model? What's the nature of the quasi-particles? Because the definition is not, at least not completely clear to me.
The quasi-particles are simply Liebniger is exactly diagonalizable by beta ansatz, and you can write your beta ansatz wave function to which particle you associate, to which boson you associate a moment, And in a sense, these are your quasi-particles.
Okay, yeah.
These are the quasi-moments. In the case of the Liebniger, quasi-particles are almost one-to-one to particles, right? Because they're just bosons with a little bit change momenta due to interaction. It's in spin chain that quasi-particles have nothing to do with spins because they can also make bound states and then they are no quasi-local.
Okay, but in Liebniger still you have, you have particles and holes. You take both of them.
Yes, I mean you have quasi-particle. You have a finite number of quasi-particles of them, or these bosons, and then you compute excitations on top of this to compute these correlators. This is just an intermediate step to see what are the intermediate states that leads to diffusion. They are scattering states, if you want.
Okay. Yep. Thank you.
So, what is the spin conductivity as a function of frequency that you have now with all this picture?
No, this is
sigma of omega. So before the first two terms is just a delta function. Now, how does it look like?
Now there are diffusive corrections.
Can you? So.
But I mean, diffusion. If you want sigma xt. But I can tell you from the point of view of dynamic structure factor, this would be something like with you do a Fourier transform with something that propagates ballistically with some k square over k square t, something like this. Not some just diffusive broadening of the dynamic structure factor.
So there's a delta function, and then the picture. How does it look like?
So you want it in terms of
no,
the Fourier transform of current correlator.
Just a picture, yeah.
Yeah. So I mean, current. Now we are saying the current correlator is a constant, okay, which is the Drude part, plus delta t diffusion constant. So this now I write it in real space. Is this a conductivity?
There's on top of it a DC conductivity.
Yeah.
So there's a Drude peak and plus a
a diffusion broadening, of course, yeah.
On top of the delta function.
Yes, on top of the delta function.
So in frequency space there's a Lorentzian, and on top of that sits the Drude peak, or?
It's Lorentzian.
I mean, just sigma primal for omega.
Yeah.
Yeah.
That's the
Yeah.
How does it look like?
But we compute it in real space. So at the moment, yeah. Yeah, okay, we can draw the picture later. Yeah, exactly. Me too. But I mean, it's just yes, a Lorentzian broadening of the yeah. It's the Drude goes in the pole, right? And then we have to discuss. I don't remember. This is the real correlation.
Anyways, I mean, yeah, we can discuss it later. But I mean, we had some predictions on that kind of many years ago, right? So on the sort of on the decay of the current correlation.
Yeah, I know your prediction, but this
and also on the frequency space picture.
Yes, but okay, but anyway, we can compare them. But these are results. Your prediction are from field theory, right? And here we have finite temperature or finite energy density.
I have a slightly different question. You started your talk with the results of Bernard and Daujon about CFTs with inhomogeneous spaces. One of the findings there is that they have a non-equilibrium steady state between the two moving out.
Sure.
Do I see that here? Because here I see a more...
No, I didn't spoke about this too much in detail, but now, yes, you have a steady state on any ray. Okay, on any x over t, you have a steady state, which is given by this particle occupation number that just tell you that it's just the left particle, the right particle, depending on the velocity. So yes, on each ray you have a steady state because you have a fixed value of of the particle content, because this is only fixed by the ratio x over t. And once you have the quasi-particle, you have access to all the expectation values.
Just a clarification when you talk about the entropy. The entropy of what is increasing? Because
The total entropy of the system.
well, okay, but the system is. What do you mean with that? How can it be increasing the total entropy?
It's just the integral of the entropy of each fluid cell.
It's closed, the system.
The total entropy.
Yeah, okay, it cannot, because the system is closed now. So
Yeah, but indeed, this is not in contradiction with unitary evolution, because this is the fact that you are producing entropy on the fluid cell. So this is just telling you that the hydrodynamic picture is not closed, right? The dynamic picture is only an evolution of the macroscopic degrees of freedom.
So how can I find this result? What I should compute in order to obtain this, to check this formula? The entropy of what?
Yeah, that I don't know. I mean, you should. You should. What? This. No. This is exact, but for the fluid cell. So you are tossing away a lot of information, right? Because you're only looking at the degrees of freedom of the fluid cell. So there is a lot of degrees of freedom inside the fluid cell that you're neglecting. That's the point. No, but look, this is hydrodynamic, right? You are going from a description in terms of macroscopic degrees of freedom, and you're coursing grain, and you're not looking anymore at the spins. You're saying now my degrees of freedom is just the quantity. No, this is just the entropy of the fluid cells. And I'm not telling you that it's exact entropy of the system, because I'm telling you that that's why it increased, because it's not exact entropy. Of course, if you really compute the exact entropy of the closed system, this doesn't increase. Just saying you that the hydrodynamic entropy increase. Okay? Because hydrodynamic doesn't control all the degrees of freedom.
Okay, are there any other urgent questions? One more question.
Quick question, which is so I thought sort of the original form of the GHD. Yeah, so in the original form of the GHD, it sort of looks like, at least in retrospect, you could think about it just from essentially non-interacting kinetic theory, but just with a suitable identification of quasi-particles.
Yeah. Yeah, exactly. And it's this part.
Right. Well, okay, yeah. I mean, that equation.
So you have
quasi-particle
move propagating ballistically with no interactions.
Mm-hmm.
And this is true. If you look at large scales, if you, in a sense, square root of t divided by t is 0, right?
Yes.
So if you look at large scales, you only see this quasi-particle moving. If you actually have to zoom in a little bit to see that there is actually a diffusive spreading.
Mm-hmm. Okay, I guess my question is, what seems different in the way that you're presenting this is that in kinetic theory, typically, I would think about getting diffusion as the statement that, you know, I started with all of my quasi-particles, but some of them weren't exactly conserved. And so I would put some decay time on the right-hand side and then try to integrate out the modes that weren't exactly conserved. And that would correct.
No, this is interesting.
Right.
Here
so,
there is no.
So here there's, but I guess here you're sort of going about it from a somewhat different.
We are not violating conservation laws. You see, this is still a divergence of something. So every conserved quantity which obtained as an integral of the quasi-particle density is always conserved.
Yeah,
so
no, I get this, but what I was going to ask is somehow is there sort of a more kinetic perspective on this where maybe you can see the diffusive corrections is kind of coming in the same way as in ordinary kinetic theory. You know, you would
But
sort of
I
integrate
don't know
out.
exactly what you mean, but isn't for you this kinetic enough? I mean, these quasi-particles are not dying, right? They are still propagating their information. So conserved quantities.
Yeah, okay, so maybe my question is slightly unclear. What I'm saying is that if I wanted just an ordinary fluid like air, and I write down the kinetic equations for air, right? So there most things are not conserved. And so where hydrodynamics would come from the Boltzmann perspective.
So you're
is
asking
that
what
you
is dissipated here?
Yeah, in some sense, could you imagine writing down not just the evolution of the quasi-particle weights, but of quasi-particle weights and some other degrees of freedom? And when you integrate out the other degrees of freedom, which do have a lifetime, you end up with the diffusive term.
Okay, that's a very good question. Up to now, no. And indeed, that's why we were a bit hesitating with the idea of using Navier-Stokes, because Navier-Stokes you always have something dissipated, right? But here we actually don't know what is dissipated.
Okay, I think we should postpone any further discussions for later. So let's thank Jacopo again for his nice talk. And with this, so the day comes to a close, and I think the bus will be leaving.